of three basic components: a primary coil, a secondary coil, and a core. A primary coil is an electrical wire. A secondary coil is an electrical wire. The core is typically a ferromagnetic material that is capable. A transformer uses the principle of mutual inductance to create an AC electrical voltage in the secondary coil from alternating electrical current flowing through the primary coil. The principle of mutual inductance says that when two electrical coils are placed near each other, AC electrical current flowing in one coil will induce an AC voltage in the other coil. This occurs because the electrical current creates a magnetic field around the first coil, which in turn induces a voltage in the second coil. A transformer improves the efficiency of the transfer of energy from one coil to another by using a core to concentrate the magnetic field. The primary coil creates a magnetic field that is concentrated by the core and induces a voltage in the secondary coil. The voltage induced in the secondary coil can then be used to drive a load. What makes the transformer useful is its ability to make the voltage at the secondary coil different from the voltage at the primary. This occurs when there is a difference between the number of times each of the coils is wound around the core. Define turns ratio. The relationship between the input and output voltages of a transformer is based on the transformer's turns ratio. The turns ratio is the number of turns, or times the wire is looped around the core, in the primary coil, divided by the number of turns in the secondary coil. Though the ratio is determined to be 2 to 1, it is usually shown as 2:1. A transformer can have more than one secondary coil. In the case shown, there are 3 different turns ratios to consider. In this situation, you would calculate each of the secondary coils separately. The turns ratio for secondary 1 is 2 to 1. The turns ratio for secondary 2 is 3 to 1. The turns ratio for secondary 3 is 10 to 1. Use the turns ratio formula and the information provided to calculate the turns ratio. In this procedure, you will calculate the turns ratio of several different transformers. In a later skill, you will use the turns ratio to determine the Describe how the turns ratio determines. If the input voltage applied to the primary coil and the turns ratio of a transformer is known, the output voltage of the secondary coil is easily calculated. The secondary output voltage of a transformer is calculated by dividing the primary voltage by the turns ratio as shown by this formula. This relationship is an important one because it helps in deciding which transformer to select for an application and can help when troubleshooting a transformer as well. First, calculate the turns ratio. Round the final answer to the nearest hundredth. Then, using the solution from the turns ratio formula, calculate the voltage in the secondary. Calculate. In this procedure, describe the functions of the four basic components of an electrical control circuit. An electrical control circuit includes the components necessary to deliver the electrical power to the point of use for an application. The four basic components of an electrical control circuit are the power supply, the input devices, the output devices, and the conductors. Power supplies are the devices that provide the source of power needed to create an electrical current. A common power supply is a battery. In electric motor control, a control transformer is usually used to supply the power for the control circuit. Input devices give the operator control of when or how current flows in a circuit. A common input device is a switch. Output devices are the components or loads in the circuit that use the electricity. A common output device is a lamp. Input devices give the operator control of when or how current flows in a circuit. A common input device is a switch. Conductors are the material through which the current flows in a circuit. A common conductor is copper wire. In order to record or otherwise communicate how the components in a circuit are connected, some sort of diagram is needed. One way to show an electrical circuit is to draw a pictorial diagram. Pictorial diagrams show us what each device looks like. However, as circuits become more complex, pictorial circuits are hard to read and hard to draw. Instead, electrical schematics are used. An electrical schematic uses standard symbols and an organized structure to show the components of a circuit and how they are connected. These simple schematic symbols can be used instead of having to sketch a battery, a switch, and a lamp.
Battery, switch, and lamp.
Many schematic diagrams will also include electrical parameters such as resistance, voltage, and current. This information can be helpful when you are troubleshooting a circuit. This circuit shows the schematic symbol for a DC power supply. Here is the schematic symbol for an AC power device. Describe the function of a control transformer. When the power for the control circuit is taken directly from one phase in neutral, or two of the phases that feed the motor, it is called line starting. When the power that is supplied to the control circuit is different than the power supplied to the motor, it is called separate control and requires a transformer to supply a different voltage. Many industrial motors operate on voltages that are higher than the voltage ratings for the control devices. To avoid running separate lines for power and control to a machine, the lower control voltage can be taken from the existing power lines by using a control transformer to step down the voltage. In this example of a control transformer, the 208 volts AC across two of the three-phase supply lines is applied to the primary of the control transformer. The transformer then steps down the voltage to 120 volts AC. The control circuit is connected to the secondary of the control transformer, which supplies 120 volts AC to the control circuit. The control transformer also isolates the control circuit from the power circuit. This means that any problem in the power circuit will be less likely to cause damage in the control circuit, and any problem in the control circuit will be less likely to cause damage in the power circuit. One common type of control transformer has two primary coils and one secondary coil. This type of control transformer is often called a dual voltage transformer because the two separate primary coils can be configured so that the transformer primary can be connected to different line voltages. In most cases, the dual voltage control transformer is used to reduce the main or line voltage of 240 volts AC or 480 volts AC to a control voltage of 120 volts AC. Notice that the primary windings are crossed. This is done so that metal links can be used to connect the primaries for either 240 or 480 VAC operation. These two examples show the metal links used to connect the primaries for 240 and 480 VAC operation. To get a control voltage of 120 volts AC from a line voltage of 208 or 240 volts AC, the primaries are connected in parallel. This is the same 240 VAC transformer configuration diagram shown earlier, except that it has been redrawn to allow you to more easily see that the primary coils are connected in parallel. To get a control voltage of 120 volts AC from a line voltage of 480 volts AC, the primaries are connected in series. This is the same 480 VAC transformer configuration diagram shown earlier, except that it has been redrawn to allow you to more easily see that the primary coils are connected in series. The reason why the primaries are connected in either parallel or series is to create a different turns ratio. To understand this, let's assume that each primary has 200 turns and the secondary has 100 turns. If these coils are connected in parallel, the effective turns of the two primaries are still 200 turns, the same as if there were only one primary. If the secondary is 100 turns, the turns ratio is then 2 to 1. This means an input voltage of 240 volts AC will create an output voltage of 120 volts AC. In contrast, if the primary coils are connected in series, the effective turns of the two primary coils in series will be 400, making the turns ratio 4 to 1. This would cause an input voltage of 480 VAC to create an output voltage of 120 VAC. Many control transformers used today have multiple taps on the primary and/or secondary coil, similar to the figure shown. This allows the control transformer to be connected to a variety of line voltages, including many international voltages such as 380 volts. Multiple tap control transformers are much more versatile than the dual voltage style transformers and are quickly gaining acceptance all over the world. Connect. The control transformer you will use has a multiple tap primary and a dual winding secondary. Select Simulator or Hardware to perform this procedure. Once you have completed one, you may go through the other. Once a transformer is installed in a circuit, it will probably operate without fail for a long time. One reason for this is there are no moving parts. If the transformer does fail, it will appear as either a short or an open in one of the coils. The two ways you can determine if a transformer has failed are: measure the input and output voltages, and check the transformer with an ohm meter. If the transformer is already connected in a circuit, the transformer can be tested by measuring the input and output voltages. If the voltages are reasonably close to the theoretical values, the transformer is good. If the voltage does not stay constant, it is usually wise to test the current levels. Although the initial voltage may appear normal, it may not hold up when the transformer is fully loaded. An ohm meter can be used to check for opens in coils, shorts between coils, shorts within coils, and coils shorted to the core. These measurements can be made without any power applied to the transformer, which makes it a safer method of testing. The resistance of each coil should be checked. The actual DC resistance of the wire will be indicated by the ohm meter reading. If any of the coils show infinity, the winding is open and the transformer is bad. A check for shorts should be made between the transformer primary and secondary coils. The primary and secondary coils should show infinite resistance between them. If a resistance is shown by the ohm meter, the transformer is shorted and should not be used. It is possible for a coil to become shorted with itself. This effectively reduces the number of turns within the coil. Shorts within coils can be found by testing the resistance of each coil. However, this check can be difficult since the resistance of each of the coils must be known beforehand. Coils shorted to the core can be found by testing the resistance between each coil and the core. Each coil should show infinite resistance between it and the core. If anything other than infinite resistance is shown between any coil and the core, the transformer should not be used. In this procedure, you will test a transformer for opens and shorts on the primary and secondary to determine if it is good.
Select Simulator or Hardware to perform this procedure. Once you have completed one, you may go through the other.
The information you need in order to size a transformer is the input voltage available, the output voltage desired, and output current required, both in rush and steady state. With this information, you can use a catalog specification sheet to select the proper transformer. The most important guideline to use when sizing a transformer is to select a transformer that will be able to safely and efficiently provide the maximum current that could be drawn by a load. A common example of sizing a transformer occurs in selecting a transformer to operate a machine. Many machines require a transformer to step down the line voltage, 480 volts AC or 240 volts AC, to the operating voltage of 120 volts AC. Machines with motors or other high inrush devices draw their maximum current when they are first started. For these machines, this inrush current is the critical value that must be considered when selecting the transformer.
If the machine does not have devices like motors with high inrush characteristics, inrush current is not a consideration. In this case, the steady-state current is more important. Most machines list both their maximum inrush and steady-state current requirements.
Transformer specification sheets usually list a rating value known as steady-state volt-amperes, VA. This is simply the secondary voltage multiplied by the secondary current, Vs times Is, during steady-state current operation.
This is the value to consider if the machine does not have a motor or other inductive load.
Another value that is also listed is the maximum inrush VA. This is the secondary voltage multiplied by the secondary current during inrush.
This is the value to consider on a machine which has a motor or other inductive load.
To select a transformer size, pick a transformer model that has a higher VA rating than is needed for your application.
However, do not pick a transformer that has a VA rating that is much higher than the rating needed. The higher above the needed rating, the less efficient the transformer will be. Pick the one that is above but closest to the required value. Caution! Caution! Never undersize a transformer. Always select a transformer that is rated above the value required for an application. Undersizing a transformer can result in serious damage to machinery or even fire.
In this
A control transformer is often used to step down the three-phase motor voltage to a single-phase voltage that can be used by the control circuit components. This is called separate control. Separate control is especially common with three-phase delta distribution systems, which have no neutral. That is why a control transformer is often found on a machine that has a three-phase motor.
In many applications, a magnetic motor contactor is also used to allow the machine to have semi-automatic or automatic control. The coil of the magnetic contactor is usually designed to operate on either a DC voltage or, in most cases, single-phase AC voltage. The coil labeled M receives its power from the control transformer through whatever input devices or switches are needed to operate the machine. When the coil is energized, the contacts of the contactor are closed to feed power to the motor. Many times, fuses are required on the primary side of the control transformer. If the control voltage from a control transformer is higher than 50 volts AC, NEC requires either that one side of the secondary be connected to earth ground or that both lines from the transformer secondary be fused.